Hello and welcome to your final lesson on our key area of photosynthesis. Today we're going to look at the limiting factors of photosynthesis. Now I've chosen a brake pedals image here because you can think about a limiting factor as something that's stopping a reaction from reaching its maximum. So our learning intention is to describe what is meant by a limiting factor, describe how to investigate the rate of photosynthesis. The rate in biology and science refers to how fast something happens. So when thinking about how fast or how much photosynthesis is happening, we're going to say the rate of photosynthesis. So name the three limiting factors of the rate of photosynthesis. So three things that will limit the maximum rate, and be able to identify what the limiting factor is from a graph. So a limiting factor is something which, if it is in short supply, prevents the reaction from reaching its maximum. So think about you're in a car, you start speeding up the car and eventually reach a maximum speed. So what's limiting you from going faster? Well, the type of car, really the size of the engine, how much mass is in the car. So obviously the heavier the car, it will be slower. If you fully load a car, it's not going to go as fast as a car which is lightly loaded. Okay, so things like the mass or the weight, the engine size, if there's a headwind, like a wind blowing against it, that's going to slow it down. So these are all different factors which are limiting you from reaching a maximum. So think about that as an analogy, and then we've got to apply that to our biology of photosynthesis. Right, so when we're doing experiments, this one we're going to investigate the rate of photosynthesis. In a valid experiment, you only ever change one variable. So a variable is something you can measure, and because you can measure it, you're able to change it. We only ever change one thing, so that we know that's the variable that we're investigating. And it's called the independent variable because it's by itself. Like when you leave the house and you grow up and you leave home, you're independent of your parents. This variable is independent of the rest. The other variables are kept the same. So let's look back to the very first lesson. We talked about light energy. We talked about how plants have chloroplasts because the chloroplasts contain chlorophyll and that traps light energy. So we need light energy for photosynthesis to happen. It makes sense then on a cloudy day, there's less light energy available, there'll be less photosynthesis. So light energy is a limiting factor for our plant. So how can we change this to investigate further? Well, if you just thought something like, okay, I'm going to investigate sunlight, okay? I've put a line through that because although it is about the light energy, it is about the sunlight, that's not measurable. How do you measure sunlight? So you have to always write a variable as how it will be measured. We'd measure sunlight as light intensity. So a high light intensity is very bright, a low light intensity is very dark. So to describe that graph, I'd say increasing light intensity will increase the rate of photosynthesis. Okay, and that seems fairly logical. So we'll go ahead and do an experiment and find out if our hypothesis is true. So our aim is the same, our hypothesis is the same. Here is our actual results as a graph. And you can see we're increasing light intensity. The rate of photosynthesis has increased as predicted, but then it's leveled off and stayed the same. Okay? And we're going to investigate why that is. So in conclusion, we'd say that increasing the light intensity increases the rate of photosynthesis until a point. Now, if the graph had numbers, I would use that light intensity number there and the units. After which, the rate of photosynthesis stays the same. So that's our conclusion. We can see here that first the light intensity is limiting it. I know that because as I increase the light intensity, the rate keeps getting higher. So therefore it needs more light. The lack of light is the limiting factor. However, in the second half of the graph, I give it more light intensity. I've increased light intensity even further, but yet the rate of photosynthesis has stayed the same. Therefore, the light intensity in the second half is having no effect on the result. So it cannot be the limiting factor. There must be something else limiting it. Does that make sense? So recap, first half, when it's going up, I know the light intensity is the limiting factor because my graph shows the more light intensity I give it, so that as I increase light intensity, I'm increasing the rate of photosynthesis. But in the second half, increasing the light intensity does not increase the rate of photosynthesis. So in the second half, the light intensity is not the limiting factor. There must be something else limiting the reaction. Okay, we also talked about the raw materials required for photosynthesis. So we looked at these images. We talked about the stomata and how the CO2 is absorbed in by the leaves of the plant. And hopefully you recognise that diagram there as the carbon fixation stage. So the hydrogen and the ATP from stage 1 are used in a series of chemical reactions to join with CO2 to make the glucose. Now, the faster this happens, the more glucose we'll get. The rate of photosynthesis here could be reduced by reducing the CO2. If there's no CO2, there's nothing for the hydrogen or the ATP to join with, and therefore there'll be no glucose. So again, if we talked about the amount of carbon dioxide, that wouldn't be correct. We don't use amount in science. I've drawn two squares here. These aren't dice. If you look at one on the left, there's 2 molecules of carbon dioxide, and the one on the right, there's 2 molecules of carbon dioxide. Now, as I'm adding more carbon dioxide within the same area, that's not increasing the amount of carbon dioxide, that's actually increasing the concentration of the carbon dioxide. So that's what I'm going to investigate as my independent variable this time. Now, if I'm changing the carbon dioxide concentrations, I've got to keep the light intensity the same this time. So there's it written as an aim. My hypothesis then, I think that as I increase the concentration of the carbon dioxide, that means there's more raw material available, that would increase the rate of photosynthesis. So my graph should look like that. I'm increasing CO2 concentration on the bottom, and that's leading to an increase in the rate of photosynthesis. So let's look at the actual results. Again, we see that at first, my hypothesis is correct, that as I increase the light intensity, this increases the rate of photosynthesis until a point. But again, after that point, the rate of photosynthesis isn't affected and it stays the same. So in the first bracket on the left, the carbon dioxide is the limiting factor. I know this because if you increase the carbon dioxide concentration, the rate of photosynthesis increases. On the second half, the second bracket, as I increase the carbon dioxide concentration, there is no change in the rate of photosynthesis, so I know that there's something else that's a limiting factor. In the second half, it's not carbon dioxide, which is a limiting factor. So again, the carbon fixation stage, as well as needing carbon dioxide to be in a certain concentration to do photosynthesis, it's also a series of enzyme-controlled reactions. Now, you'll learn about enzymes later in the course, but for now, just believing that enzymes are affected by temperature. Okay, so changing the temperature affects how well the enzymes work, and that'll affect how fast this process, this cycle happens. Okay, so this time my independent variable is going to be temperature. That means I'm changing the temperature for each repeat of my experiment, and because I can only change one variable, that means I'll be keeping the light intensity and the carbon dioxide concentration the same. So there's my aim. Now, if my hypothesis is that increasing the temperature will increase the rate of photosynthesis, then my results graph will look like this. As the temperature on the bottom increases, the rate of photosynthesis increases. So I'll carry out the experiment and find out what actually happens. So in my results, my graph's actually a bit different from my hypothesis. At first, it's the same. As I'm increasing the temperature, the rate of photosynthesis does increase until a point. However, increasing the temperature further actually decreases the rate of photosynthesis. So, temperature here is a limiting factor either side of the maximum, okay? Okay, so how do we identify the limiting factor? Okay, so look at this graph. The independent variable is the units of light intensity, and they're using that to find out the rate of photosynthesis. Now, the general trend, if you increase the light intensity, the rate of photosynthesis is increasing until a point after which it remains the same. So if I throw this red line in here, look at the purple line that's going up before the red line. So to the left of the red line, what's the limiting factor? Well, the purple line's increasing up the way at this point from 0 to 5.5 units of light intensity. So therefore the light intensity is a limiting factor, because as you increase it from 1 to 2, 2 to 3, 4 to 5, it's increasing the rate of photosynthesis. However, to the right of the red line, so from 5.5 onwards, light intensity is no longer a limiting factor. Something else is preventing the rate of photosynthesis from being higher. Okay, so if I add this blue line in here, you can see that the green line and the purple line have deviated. So if we look at the light intensity at 8 units, the rate of photosynthesis is no longer increasing for either line. So it's not the light intensity is a limiting factor. So why is the green line not as high as the purple line when they both have 8 units light intensity? Well, look at the key at the bottom. The green line has 0.03% carbon dioxide concentration, whereas the purple line has 0.1, which is higher. So therefore, the purple line is higher because it has more carbon dioxide concentration. So therefore, between the purple and green line, the concentration of carbon dioxide is the limiting factor. Let's look at that again. So here's a results table the aim is to investigate the effect of light intensity and the rate of photosynthesis. Now, a few things here to learn. With a results table, the first thing that's given is always the independent variable. That's what goes on the x-axis on the bottom of a graph. So they're changing light intensity from 10 to 20 to 40 to 60 to 80%. They're recording the rate of photosynthesis. And you can see that they've done one repeat and then they've done a second repeat, okay? If you repeat an experiment, it increases the reliability because you can calculate an average. And that's what they've done here in bold. So we have the average rate of photosynthesis for each light intensity. This is what we're going to put as the dependent variable on the y-axis. So we turn that in the graph. Things to remember for graphs, how you get marks. First of all, what's been changed by the scientist is the first thing in the table, the light intensity. That must go at the bottom, okay? Because it's causing the result. The dependent is the result. It depends on what's happening at the bottom. So it has to be on the y-axis. And we only plot the average. Look at the plotted line. As the light intensity is increasing, the rate of photosynthesis is increasing until a point, after which, if you increase the light intensity, the rate of photosynthesis stays the same. So what's happening here? So at point A, the results line, the dotted line, is increasing. So remember the rule of thumb. If the line is going up, your answer's at the bottom. So if it goes up, you look down. So at A, the limiting factor is light intensity. That's a common exam question. They might show you a graph like this and say, what is the limiting factor at A? If you look at A, the line's going up, you look down and you get the answer at the bottom. So the limiting factor at A is the light intensity. At B, the light intensity is no longer a limiting factor. And I know that because if I increase the light intensity further, there's no increase in the rate of photosynthesis, it stays the same. So at B, I can rule out light intensity. It's no longer the limiting factor, and it's one of the two other limiting factors. So it's either being limited by the temperature or by the carbon dioxide concentration at point B. Again, it could be shown like this. So again, at point A, you get the answer from the bottom because the line's going up. So at A, the line's going up, look at the bottom. At A, light intensity is the limiting factor because, you know this, because A goes up further if you increase the light intensity. At B, there's no impact on light intensity. You can keep increasing light intensity at this point and it's doing nothing to your results. The rate of photosynthesis stays the same. So the answer at B would be the difference between it and the line below. So what's the difference between the blue line and the dark line? Well, they've got the same light intensity, so the other difference is always given to the side here. So either be temperature or CO2. Look at the question, there'll be information on it, there'll be something less about that blue line. Okay, so let's look at how you can investigate the effect of light intensity and the rate of photosynthesis. You cannot see the rate of photosynthesis, so you have to work out a way of finding this out. To change the light intensity, you could have the lamp set at different power settings or use different bulbs, but an easier way is actually to change the distance between the bulb and the plant. So if you decrease the distance, it's closer, the light intensity will be higher. If you increase the distance, it will be further away. So that's one way we could set this up. How do you think we'd calculate the rate of photosynthesis by looking at this diagram? And the clue's there if you look carefully. You could count the number of bubbles. What's being given off by the plant during photosynthesis? What gas is released by the plant? Oxygen. Therefore, the more bubbles of oxygen released in a minute, the higher the rate of photosynthesis. Here's a bonus question. Why do you think that the test tube with the plant in it is also put in a beaker of water itself? Why not just have it on a test tube rack and move it that way? Well, if you think about moving a test tube with a plant in it closer to the light, you're increasing the light intensity, but the light would start to warm up the test tube, so you'd also be increasing temperature. Now that's a problem, you cannot change two things. Temperature must be the same each time. So by putting it in a beaker of water, you're trying to keep the temperature the same. The light will pass through the water in the jar, the beaker, into the plant, but the water in the beaker will absorb any temperature change and prevent the plant from changing temperature, and you've got a thermometer there to make sure the temperature is being kept the same for each repeat. That makes it a valid experiment. So a lot going on there. How we change the light intensity by using distance, how we get a rate of photosynthesis by doing counting the number of bubbles per minute, and has to be per unit of time because it's a rate, and the use of the water and the thermometer to keep temperature the same. Another way of doing that actually would be to put a plant in a funnel at the bottom, and then you fill a test tube with water right to the top and put it on top. The test tube collects the bubbles of oxygen, And as more oxygen is being collected, it displaces the water. So the water that would be filling the test tube is pushed down the way, and then you can actually measure with a ruler how much oxygen has been trapped at the top. Okay, valid experiments mean we only change one thing. If my independent variable is the concentration of CO2, which two jars would I want to use? Pause now and answer. Press play when you want to find out if you were correct. Okay, so the answer to the question is, I'm only changing the concentration of CO2, so I'd want to use A and B. They both have light, be the same, they both have the same volume of water. The only difference is there's no carbon dioxide in A and there is carbon dioxide in B. So we compare A and B that way. So this first one shows the effect of increasing carbon dioxide on the rate of photosynthesis. So our independent variable is carbon dioxide. It's been changed, it's an x-axis, so we can find out about the dependent variable, the rate of photosynthesis. Okay, so two factors which could be limiting it between x and y. What do you think? So pause the video now, try it yourself, and then press play when you want the answer. Okay, so to do this, between x and y, the rate of photosynthesis is staying the same, so I've ruled out carbon dioxide. Carbon dioxide was a limiting factor, but not after point x. So the other two, if we look down the options, the other things we learned from the course were temperature and light intensity. So that would be answer B. Okay, in this question you've got a setup. We're carrying out into different conditions required for photosynthesis. So you've got to think about what you need for photosynthesis. Before it, the 4 plants were de-starched, so all the starch has been removed because they've been kept in the dark for a day. The plants were then placed in the conditions below and left for 48 hours. The leaves of each were then tested for starch. So which of these 4 boxes would have starch after 48 hours? Would it be the control, which is in a transparent box? Experiment 1 is a transparent box but with a chemical which absorbs CO2. Experiment 2, a black box so no light can enter with a chemical to absorb CO2. Or a black box without the CO2 absorbing chemical, which is experiment 3. So pause now and think which one would have starch in its leaves after 48 hours. Press play when you want the answer. Okay, so the first thing I'm going to do is rule out experiment 1 and 2. This chemical is going to absorb CO2. If there's no CO2, there will be no photosynthesis, therefore there will be no glucose to turn into starch. So these 2 plants will not have starch in their leaves after 48 hours. Because it's in a black box, there will be no light either. And without light energy, also you cannot have photosynthesis, so there will be no starch. So my answer is going to be the control, because it has the CO2 in the air around about it, because there's no chemical to absorb it, and it's a transparent box, so the light energy is going to get through. Okay, last question, looking at the rate of photosynthesis. It's a result table. It wants to know which change in light intensity produces the greatest increase in rate of photosynthesis. You can always use a calculator in biology. I would always encourage you to show your working down the side so you can go back and check your answers. So go ahead, try this in your jotter, press play when you want, pause it, and then press play when you want the answer. Okay, so I've done each one. The first one in kind of purple, from 10 to 20, the increase in the rate of photosynthesis is from 2 to 28. So 28 take away 2, that's a plus 26 increase. From 20 to 30 in the green, it's increased by 25. From 30 to 40 in the red, it's gone from 53 to 76, so it's gone up by plus 23. And finally in the blue, from 40 to 50, the rate of photosynthesis has gone from 76 to 85, so that's plus 29. So now I've done the maths, it's quite easy to see that plus 26 is the greatest increase, so the answer would be A, from 10 to 20. Okay, so the line intention. Okay, hopefully you paused the video on the learning intentions and tried to answer them yourselves. Pause again now and you can check your answers against the work shown here, okay? This is all we need to know for lesson 4 and that's the end of the lesson.